For our experiment, we decided to measure centripetal force. Our variables in this experiment were mass, radius, velocity, and centripetal force. The equation we used to find centripetal force was mass times velocity squared divided by radius. We chose to do this experiment to see what effects radius would have on velocity as we changed the radius in each trial. Our constants were the mass at the top, which equaled 0.0142 kilograms, and the weight at the bottom, which equaled 0.425 newtons. Our independent variable was the radius. We measured the radius by starting at 0.45 meters and decreasing it by 0.04 meters on each trial. Our dependent variable was the velocity, which we found by multiplying the number of revolutions times the circumference and dividing it by 10 seconds, which was our time in each trial.
Okay, so this is our first trial, and we have a radius at 0.45 meters, and that's measuring from the top of the PVC pipe to the hanging mast. We have 4 centimeter increments, but we're not going to use those yet. And basically what I'm going to do is I'm just going to start swinging this over my head until I get this length to stay at the same, so the radius will stay constant. So I have this. And you can notice that even though I'm spinning it, the PVC pipe still stays. It's keeping this from moving, and I have to hold it. Okay, ready?
Go.
Okay, so I counted about 14 revolutions, and that was 10 seconds right there that Abrianna just timed. So that's 14 revolutions per 10 seconds, and we're going to use that in a formula that we're about to plug in. Okay, so we've used this 14 revolutions per 10 seconds, and we've plugged it into a formula. So we're going to find the velocity, because velocity is going to be measured by distance over time. So we have the distance, which is going to be the radius. We're going to use the radius and plug that in to find the equation for the circumference, and then multiply that by the revolutions and put it all over 10 seconds to find how many meters per second the mass at the top was traveling. So we have 2 pi times 0.45 meters, which is the same as 2 pi r. That's 2 pi times 0.45 meters times 14, which is the number of revolutions we had. And we put all of that over 10 seconds because we counted for 10 seconds, not 1. And we found that to be 3.96 meters per second. A few trials on our own, but we're filming this one because it's about in the middle. So this is our 6th trial in, and we have it at 0.25 meters right now, and that's again measuring from the top of the PVC pipe to the hanging mast. And we're going to do a very similar thing to last time. We're just going to swing it around and count how many revolutions per 10 seconds there are. So I'm going to go ahead and start swinging this above my head. Okay, ready?
Go.
Okay, so I counted 29 revolutions, and we're going to plug that into an equation again and explain to you what we've done. Okay, so for this trial we had 29 revolutions with a radius of 0.25 meters. So we plugged our 29 revolutions per 10 seconds into our equation, which was the circumference 2 pi times the radius 0.25 meters times the revolutions 29. We put that all over 10 seconds, and we ended up getting a velocity of 4.56 meters per second. So for this one, this trial, we have a radius of 0.09 meters. And again, that's measured from the top of the PVC pipe to the hanging mass. This one's really difficult because the radius is so small.
Go.
Okay, so for our last trial, I counted about 85 revolutions, which is probably a bit off, but we went ahead and plugged it into the equation because that's what I counted when we did it. Now, I'm going to have to hold it right here in front of my face so you can see it. But we plugged that into our equation, which was our circumference, 2 pi times our radius, 0.09 meters, times our 85 revolutions, all over 10 seconds. So for this trial, the velocity equaled about 4.8 meters per second.
Here's a detailed drawing of our diagram that we used for our experiment. We used the PVC pipe to keep our hand and the string from being in contact with each other, so you wouldn't have unmeasurable force. And we used a bottom mass, which were washers, and a centripetal force of 0.425 newtons. The washers at the top had a mass of 0.0142 kilograms.
So this is our graph of our experiment. It turns out our data that we collected was pretty off, and that could have been caused by maybe the radius changed while we were collecting data, or various other factors. The black dots represent our data that we collected, and the blue dots represent, right here, the blue dots represent what around what we should have gotten. We found the equation for the blue dots by using the centripetal force equation. So centripetal force is equal to mass times velocity squared all over radius. So we plugged in our numbers that we had, which were our constants. So 0.425 newtons is equal to 0.142 kilograms times velocity squared over radius. We multiplied both sides by the radius, so we had 0.425 newtons times the radius is equal to 0.0142 kilograms times velocity squared. Then we divided both sides by the mass, which was, again, 0.0142 kilograms, and set that equal to velocity squared. Then we simplified this fraction and took the square root of both sides, so we got the equation to be 29.93 newtons per kilograms times the radius is equal to velocity. Once we plugged that into our calculator and found the data, we found these blue dots here. The slope is force over mass, so that means that the meaning of the slope is the amount of force required to move 1 kilogram of mass. And this is a clear look at the equation I was talking about, so you can see clearly all the steps that we took to find the correct equation, and it should be the square root of 29.93 newtons per kilograms times radius is equal to velocity. Okay, so this is a better look at our graph. These are the blue dots I was talking about in the video. That's what the equation should be, and these black dots up here, I don't know if you can tell they're black. These are that's the data that we collected. Clearly it's really off, and I'll explain why later. Okay, so clearly the graph that we showed you guys, the actual equation and the graph of the numbers we got were very off, and that could have been caused by a number of things. A lot of things could have gone wrong while we were recording our data. We could have just changed the radius maybe while we were spinning it. It could have, the weights, the mass at the bottom might have pulled down a little bit too much and the radius could have shortened, or vice versa, and it could have lengthened. And I could have spun it at a different rate, or I could have just simply counted the revolutions wrong. But that was the data we collected. Luckily, we found out what the data should have been, which again was the square root of 29.93 times the radius, and that the graph of that equation should have been what our data looked like.